Dear students, in today's lecture we will study about the synchronous generator operating alone. In this lecture we will study how the generator will operate if the generator is connected with the load alone, or what is the difference if the generator is connected with load having some other synchronous generators connected in parallel. So first of all we will study the behavior of the synchronous generator under load varies depending on the power factor of the load. This is the one thing, and the other thing is on whether the generator is operating alone or in parallel with other synchronous generators. So two main factors are there. One is the power factor of the load, and the other factor is how the generator is operating, whether it is operating alone or whether it is operating uh, in parallel with other generators. In this lecture we will study the generator operating alone with simplified phasor diagrams, ignoring the effect of resistance, armature resistance, Ra. Since we studied in the last lecture that Ra is quite small with respect to the X, so we can neglect the value of R to simplify our calculations. The speed and the rotor flux of the generator is assumed to be constant. We will discuss this in detail in coming few slides. We will understand the effect of load changes on a generator operating alone. That if how we change the load, like we uh, increase or decrease the value of load, and what will be the effect of this load changes on the generator. The speed of the generator omega is constant and the field current IF is constant, which means the voltage EA would be, since we know that this is equal to K phi omega, will also be constant, since the two variables in this equation phi and omega are assumed to be constant in this case. Consider the three different types of loads connected and analyze the effect of changes in the loads. So we will consider three different types according to their power factors, whether the power factors of the load is leading, lagging, or it is unity power factor. The effect of load changes. So as we have just discussed that there would be three kinds of loads. Lagging load, which deals with lagging power factor, unity load, and leading load. First of all, we discuss the lagging load. If lagging loads are added to generator, V phi and the terminator voltage Vt decreases significantly. So here is a V5. If the load is increased while keeping this condition of lagging load and the value of the load is increased, then the new value of V5 would be decreased. Although it is in line with V5, but V5 bar is slightly decreased. Similarly, we can see but the current IA would be slightly increased and it would also be having the same angle with V5 and also in line with IA. So IA bar is also in line with IA. In the case of unity load, if unity power factor loads are added to a generator, there is a slight decrease in V5. So if this was a V5 and we have increased the load, the new V5 which is V5 bar would be slightly decreased from the previous value, as you can see from the phasor diagram. But if the load is leading, in that case, if leading load are added to a generator, V5 and Vt will rise. This is how we see that V5 before increasing the load was here, but after increasing the load, V5 bar would be increased. The main factor which is used to compare the voltage behavior of two generators is voltage regulation. We have discussed this formula many times ago in previous lectures, that voltage regulation is a factor, is a benchmark to compare different generators, where VNL shows the voltage with no load and VFL shows the voltage with full load. Voltage regulation under various load conditions. So we discuss the three conditions. If we have lagging power factor, the large positive voltage regulation would be. In the case of unity power factor, the voltage regulation would be small positive. In the case of leading power factor, it would be negative voltage regulation. So it is desirable to keep the voltage supplied to the load constant even though the load varies. So the main point is that we want that the voltage should be applied to the load is constant, and we want that it should be constant. But sometimes the load itself changes, varies. It can be decreased or increased. But even then, we want that the supplied voltage should be constant. To do this, this can be accomplished by controlling the flux of the machine. So if we can control the flux of the machine, we can make the supplied voltage constant according to our situation. Suppose that a lagging load is added to a generator. If lagging load is added to a generator, then the terminal voltage will fall. To restore it to its previous level, decrease the field resistance Rf. If Rf is decreased, then If will increase, and when If is increased, it will increase the flux phi. If phi is increased, since we know that EA is directly proportional to phi, if phi is increased, EA would increase, or you can say that internal voltage EA would increase. So an increase in EA increases the terminal voltage. So we can regain our lost voltage or decreased voltage by this way. The process can be reversed to decrease the terminal voltage of the generator if we want to do that. Now we will go through an example where a 480 volts 60 Hz delta connected 4-pole synchronous generator has the OCC shown in the figure. So this is the figure in which OCC diagram has been shown, and this diagram, this graph would be helpful in calculating the values of current according to our requirements. This generator has a synchronous reactance of 0.1 ohm and an armature resistance of 0.015 ohm. At full load, the machine supplies 1200 ampere at 0.8 power factor lagging. Under full load conditions, the friction and windage losses are 40 kW and the core losses are 30 kW. Ignore any field circuit losses. So we have to answer these 6 parts in this example. In first part, the speed of rotation of this generator is to be calculated. In second part, how much field current must be supplied to the generator to make the terminal voltage 480 volts at no load. So we will see how we have done this. If the generator is now connected to a load and the load draws 1200 ampere at 0.8 power factor lagging, how much field current will be required to keep the terminal voltage equal to 480 volt? How much power is the generator supplying? How much power is supplied to generator by the prime mover? So what is the machine overall efficiency? In this case we will find the value of eta efficiency. If the generator loads were suddenly disconnected from the line, what would happen to its terminal voltage? And then finally, suppose that the generator is connected to a load which is drawing 1200 ampere at 0.8 pf leading. how much field current would be required to keep the VT at 480 volts. So now we will calculate every part separately and in detail. So this is the solution where in first part, if we want to know the rotation of this generator, the relationship between the electrical frequency and the mechanical rate of shaft rotation is given by this formula as we have studied earlier. So the Nm can be found by taking it to the left and putting the value of Fe and P, since we know there are 4 poles, so putting the values over here we can get the value of Nm. In B part, how much field current must be supplied to the generator to make the terminal voltage 480 volts. So if this is 300, 400 and 500, so 480 will be somewhere over here. So at the 480 volts, the answer of the current would be, it would be somewhere 4.5 over here. So this would be approximately 480 volts. And so from this OCC, IA would be 4.5 volts. So in third part, if the generator is now connected to a load and the load draws 1200 ampere at 0.8 pf lagging, how much field current will be required to keep the terminal voltage equal to 480 volts? The armature current is 692.8 ampere. By putting these values of IA and the given values of RA, X and V phi, we can find the value of internal voltage EA, such as 532 is the magnitude with the angle of 5.3 degree. From the phasor diagram, it can easily be verified. But to keep the terminal voltage at 480 volts, EA must be adjusted to 532 volts. From OCC, the same diagram, the required field current would be 5.7 ampere. So if we see 532 somewhere here, so it would be 5.7 ampere somewhere, some point over here, 5.7 ampere. Now we come to the fourth part, D part. How much power is the generator supplying? So we want to calculate P in. How much power is supplied to the generator by the prime mover? What is the machine overall efficiency, eta? So first of all, we find what is the P out. Since we know the formula of P out, we find the value of P out. If we know the value of P out, then we can easily find P in by adding losses to the P out. Then the P in would be the total power. So If we want to calculate P in, so P out plus all the 4 losses we have connected, we have included all the 4 losses, so it will give us the P in. By putting the values, we calculate the losses, and we can calculate P in as 889.6 kW. By using the values of P in and P out, we can easily calculate the efficiency of the generator from this formula, in which eta is showing the efficiency of the generator. So in this case, the efficiency is 89.75, or almost 90%. In part E, we see that if the generator loads were suddenly disconnected from the line, what would happen to its terminal voltage? As the current would as the generator loads were disconnected, the current would drop to 0, and making EA is equal to V phi, which means if there is no current or no load, then the internal voltage would become equal to the terminal voltage. So we also discussed this in detail in previous lecture, that EA would be equal to V phi if there is no load or no current. Since the field current has not changed, the magnitude of EA has not changed. V phi must rise to equal EA. Therefore, if the load were suddenly dropped, the terminal voltage of the generator would rise to 532 volts. In F part, which is the last part, finally suppose that the generator is connected to a load which is drawing 1200 ampere at 0.8 pf leading. How much field current would be required to keep the VT at 480 volts? First of all, we find the internal voltage EA, as we found out in previous cases. By finding the value of EA, and we want to keep the VT is equal to 480 volt, the internal generator voltage EA must be adjusted to provide 451 volts. Using the open circuit characteristics, which is OCC, as shown in the diagram, the field current would have to be adjusted to 4.1 ampere. You can easily see that at 450, somewhere 451 volts, the current would be 451. It would be something 4, around 4 or 4 point something. So this is for today. Thank you.